On to another most unusual wave behavior. We are going to talk about interference. Now notice we talked about diffraction, which was a very unique wave behavior. Interference also, that's why the asterisk is here. So we're on notes page 19, what do periodic waves do? And now we're rounding out the major behaviors of periodic waves. Remember, periodic were regularly repeating, symmetric waves. So we talked about that waves travel, of course. Waves sometimes get absorbed, like when you're wearing that black shirt on a hot day. We talked about waves reflecting. So when they're in one medium, they meet a boundary with another medium and bounce back into the first medium. We talked about the fact that every time a wave meets a boundary, TAR happens. A transmission, some goes into the new medium. Absorption, some of the energy gets lost to the medium. And reflection, some of it bounces back. Now, these are divvied up differently depending on the actual media. Depends on what it is you're traveling through, the waves traveling through, and what it is it bumps into. And they're designed that way on purpose. For example, a mirror is designed to maximize reflection, whereas there are certain barriers to ocean waves that are designed to maximize absorption. Okay, windows are designed to maximize visible light transmission. We also talked about refraction, which was just a special case of transmission, which is when you travel from one medium into a new one. And we had kind of like this image here. We had that bending of light, speed and wavelength generally change. And we also talked about diffraction, which was very unique to waves. And that's the waves spreading out, either around a barrier or passing through a narrow opening and spreading out. And that's why things with longer wavelength like sound, they always come get you. You can't really hide from them. Finally, we're going to talk about interference. So what is interference? Interference is definitely a unique wave behavior. The wave interacts with other waves in the medium. That by itself does not sound unique. Okay, it interacts with other waves. Great, people interact with other people. Baseballs interact with other baseballs. But the nature of the interaction is unique. By the way, if you need to remember all these wave phenomena, as far as Gump would say, a wave is as a wave does. TARD. Transmit, absorb, reflect, refract, diffract, interfere. And we'll talk about a few other phenomena, and generally they can be understood by some combination of these. All right, so let's jump over to our page on interference. Where is that page? Here we go, page 31 in your notes. What does interference look like? All right, so here's an interesting question right here. So waves transport energy, not mass. That's important. Because of this, two waves can occupy the same volume of space, the same location at the same time. Particles cannot do this. For example, if you have two baseballs and you throw them at each other, here they are, two baseballs, you throw them at each other, what happens? Do you still have two baseballs that hit each other, or do they suddenly morph into a large baseball? Well, which one of these is more reasonable for waves? Well, let's check it out. So right here, example 27, we're going to do a lump coming towards a lump. You can kind of think of this as a pulse or a crest coming towards a crest, A and B. They're both the same width, they're both the same height, and because these two are both looking the same but heading toward each other, we call them in phase. Another way you call that is 0 degrees out of phase, but in phase. So here they come. What happens when they hit each other? That's the question. Well, we got a little video that's going to help us out with that. Here we go. Here's our video to help us out. What happens when two pulses that are in phase approach each other? So let's check it out. Jump up a little bit. Mr. Gruber helped us out. So first, what you'll see, let's back up, back up, back up. You can tell by the little time bar here whether this is going forward or backward. So he created two pulses. They look roughly same width, same height. If you notice where they line up, their heights are roughly around the V, the nook of his lanyard. Now, when they meet, what happens? What? Do we see one big wave? Why, yes, we do. One big wave. Oh my goodness, baseballs certainly do not do this. Baseballs certainly do not make one big baseball, yet here we have one big wave. That is interference. these waves actually combine. But wait, it's not done yet. Watch the little time bar here. I'm going to keep going forward. And what emerges? Two waves again. So they made one big wave, and then they emerged as two little waves. Oh my goodness. And you may say, oh, look, but they're lower now. Not really. The whole device, if we had this, I'd show it to you. It's at school. The whole device actually tipped toward the camera. So these, think of this as the baseline here, and there's the height of the pulse. There's the height of the pulse. Here's the new baseline because the whole device tips. And actually, their heights are just like they were before. Just the whole device tipped. So interestingly, you make a bigger wave, and then afterward, you get your two little waves. Oh, that's really interesting. So let's get the details of this. So mid-collision, we get a big wave. So really want to know the height and the width of that wave. You can get a rough idea of this by checking this out. The width, actually, these were supposed to be roughly the same width. If you do count them up at 1, 2, 3, 4, 5, 6, comes out to about 17 bars wide. So is this one. And when they make a combined wave, you also get like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, something like that, about 17 bars wide. The width hasn't changed. They've kept their widths, but the height, if you want to look maybe from the loop to the nook, and now the loop to the nook to all the way up here, up by the nook of the zipper, the heights have added. So what's gone on here? Here we go. For these two in phase, you get right in the middle where they meet. I'm going to try to do this carefully. This has a height of h. So does this one. This has a width, let's call this of w. So does this one. And you can write it next to it if you'd like. And there we go. The combined wave, the interfered wave, will actually still have a width of w. In this case, they have the same width, so about this, except the height now will be actually not h, but h plus h. And I'm going to call this h plus h instead of 2h, because really that's how it comes about. H plus h. And so this wave now will look something like this. Cool, there's the wave. And then post-collision, we saw you actually had a lump over here. You had a lump over here. And one of them was traveling this way, and one of them was traveling this way. And they still had, I'll change the color so we can see it, they still had a width of w. And because the whole device tipped, it's a little harder to see. But if you look at it carefully compared to the baseline, they still had a height of h. However, the one thing we couldn't tell is which was which. Which was which. Did these pass through each other, or did these bounce off of each other? So did A and B come to the center, boom, and then separate? Now this is B, this is A, or did they pass through each other? In class, I'd have you do a little predicting on how to figure this out, but I'll show you a way we can do it. By the way, this process of taking two smaller waves in phase, combining them to make a bigger wave, this is called constructive interference. This is when matching parts of interfering waves meet, resulting in a wave with a larger amplitude. That makes sense. They match, meet, make a bigger one, and then we have two smaller ones after, although we're not sure which is which just yet. So we could call this one up here, this is A plus B. Put a little heart around them. It's A plus B. And then which is which, A and B down here? Well, we'll find out shortly. Okay, so the other video that's going to help us out to figure out this mystery of which is actually this one. This is our out of phase video. So what's going on with our out of phase video? Well, in this video, instead of sending two crests at each other or two up pulses, we're going to send an up and a down, like a crest and a trough, we call this out of phase. In fact, these are in particular 180 degrees out of phase. Put a little 180 over here. This is 180 degrees out of phase. And this one was in phase. We also call that 0 degrees out of phase. Okay, anyway, back to it. So what happens? When these two meet, A is coming toward B, B towards A, what happens? Let's see, constructive, we don't need you anymore. Here we go. Let's see, let's play the video. You can watch the little bar here to see what's happening. So Mr. Gruber sends, here we go. So if you notice, backing up. All right, here we go, forward. On our left, you see a crest, an up pulse. On our right, facing us, you see a trough, a down pulse. They're coming toward each other. What happens when they meet? Flat line. Cold. Flat line. These two did exactly what happened before here. In fact, let's draw it out. What happened mid-collision? Sorry, my line's not that flat. Flat line. Oh, that's pretty neat. So what we had here is we had our height, h, and this one had a height, also h, but you could call it negative h, just to pay attention to what we're doing here. And then, what happened when they met? Well, let's switch up the color. They still had a width w. And you know what? When they met, their width was the same. The width is still right here. That's about it. That's this width also. And actually, we have it right here. What is this one? It's just as we said before, and this is why I did not have you say 2h. The height of this one actually is, this still is a plus b. Here it is. It's a flat line. And this is still, the height of this one is still h plus, and in this case, it was negative h. And of course, that comes out to a height of 0. So this one equaled 2h, this one equaled 0, but that's why we didn't just jump to 2h. It's a sum. And so what happens post-collision? Well, you probably will know. So let's back up just so we know we're not messing around. Here it comes, come. Boom, disappear. And that's why we call it destructive interference. But watch afterward. Well, there they are again. And there they go. And if you notice, on our left is now a trough, and our right is now a crest. That's reverse from how it started. Just to go back and show it to you again, we're going in reverse. Now let's go forward. Look at that. From our perspective, crest on left, trough on right. Destructively interfere for a flat line, and then trough on left, crest on right as they go away. So post-collision, this one actually looks like this. Down. Sorry, our drawings are not so good. Up. And this one is heading this way. And this one is heading this way. And they still have that width W. And this one still has the height of negative h. And this one still has the height of positive h. And so from this we can tell which is which. Well, this is still wave B. This is still wave A. And that actually allows us to go back over here, which means the waves literally pass through each other. Far out. So this one is B. This one is A. This is what we call on the right-hand side destructive interference, when non-matching parts of interfering waves meet and result in a wave with smaller amplitude. And this, in a very real sense, should kind of shake you up a little, like, whoa, waves are different. Baseballs, when they come together, they hit and bounce off. They never turn into a big baseball. They hit and bounce off, and the one that came in from the left will bounce back off to the left. The one that came in from the right will bounce back off to the right. Waves, on the other hand, will come, they will meet and combine, and then keep moving as if they never met. That's amazing. Pass right through each other. That's one of the joys, or one of the privileges of transmitting energy but not mass. It's funny, you know, if two surfers were following the waves, if they came and met, I've got to find a video of that. That must have happened. Surfing waves that are bringing them in opposite directions. You got to have kind of diagonal cross waves. And if they met, the waves would pass through and keep on going. But the surfers most certainly would not. They would crash and fall. Out of phase, notice, they meet, they destructively interfere, and they keep going on their way. This would be like a baseball and an unbaseball. If they met, do you still have the two baseballs, a white and a black baseball, versus nothing at all? Waves, you'd have nothing at all for a moment, but you just can't have them with baseballs. All right, quick view over here. This is a simple task. So you have to mark 5 C's and 5 D's. What do I mean by C's and D's? C is constructive interference. We were writing that with red up top. D was destructive interference with blue. It's harder for me to write letters, so I'm just going to put little dots. This is the aerial view. Aerial view means from above. From above, if we look only at source A, it's rippling the water, like throwing a rock in a pond, and you're getting wave fronts. Here's a row of crests. Here's a row of troughs. Here's a row of crests. If you dropped another rock in a pond nearby, you'd also get another source of circular wave fronts. When these two are near each other, they overlap. So what happens at the point of overlaps? Well, whenever you have a black line, solid line, which is a crest, overlapping with a crest, you'll get constructive. So right here, everywhere I put red, it's going to be constructive. Constructive, 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 constructive. Whenever you see those two solid lines cross, it's a crest and a crest. It's this picture, but instead of the profile view, it's the aerial view. Constructive, constructive. Where else we got any more here? Point P is constructive. Those are not the only constructives. When a trough and a trough overlap, it is also constructive, 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 constructive. Cool. Where a crest and a trough overlap, you're going to get max destructive. So right here is destructive, 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 destructive. All around here. Destructive, destructive. Any more? Yeah, here. All these destructive interference, destructive interference, destructive interference. What's pretty cool is they actually trace out these patterns. You start to see kind of like here, these neat sort of crosshash patterns. All right, so what's the end result of all this? That's the important part here. For sound, constructive and destructive interference. Remember, this is all about the amplitude. It's all about the amplitude, baby. Here it is, all about the amplitude. The amplitude of sound was volume. So for sound, you're going to get louder and quieter noises. Light, again, it's all about amplitude. This happens with light too. In fact, you saw that pattern from those little diffraction glasses when you saw the grid pattern of lights, which we'll talk about more later on. That also, why was it light, dark, light, dark, light, dark? Because what you didn't realize is there were lots of slits in those glasses, which means the light went through and created multiple sources. So for light, constructive and destructive interference result in brighter and dimmer images because amplitude is brightness of light. Some cool demos to do with this. Actually, a tuning fork is a fantastic demo by itself because a tuning fork has two ends and each end is making sound. And so depending how you orient it, you can hear it, but no tuning fork. If you get a hold of one, ping it, put it by your head, and slowly rotate it, and you'll know what I'm talking about. It's pretty neat. It goes loud, quiet, loud, quiet. All right, let's check this out. So let me go back here and just point one thing out. We picked basically the simplest possible cases. Same width pulses, same height pulses, and send them at each other. These can be different widths. These can be different heights. You can have multiple pulses. In fact, you could have periodic waves doing this. So this can get extremely complicated quickly. So how do you come up with the shape? I mean, these two are easy. 1 plus 1 equals 2. 1 plus negative 1 equals 0. No problem. Same width. Make it easy. But how would we do this if we wanted to combine, let's say, wave A and wave B right here? That's a little tougher. That's where the principle of superposition comes in. And realistically, computers are doing this for us. But we still should understand how they are doing it and what they are doing, and we can still do it in simple cases. So, principle of superposition. You get two waves going through each other, two waves interfering. The resultant wave, in case that's not clear, this mid-collision was the resultant wave. The resultant wave is found by adding the displacements of the individual waves point by point. Sounds like a mouthful, but the truth is it's really easy. Check it out. Watch how easy this is. Go to the first grid point here. A is at 0. B is at 0. They're right on the axis. What's 0 plus 0? Boom, 0. There's your first resultant wave data point. Go to the next grid. B is at 2. A is at not 1 or 2, but 1.5. 2 plus 1.5 is 1, 2, 3.5. Boom, put your next grid point. Go to the next one. B is at 0. A is at 2. 0 plus 2 is 1, 2. Your next resultant wave point is at 2. Starts to come out looking a little funky. Next one, B is at negative 2. A is at positive 1.5. So negative 2 plus 1.5 is negative 0.5. So come down here, put a dot. All right, go to the next one. B is at 0. A is at 0. Oh, there we go. 0 plus 0 is 0. Next one, B is at 2. A is at negative 1.5. Add them, you get 2 plus negative 1.5 is positive 0.5. Next, B is at 0. A is at negative 2. 0 plus negative 2, negative 2. And then A is at negative 1.5. B is at negative 2. Negative 1.5 plus negative 2 is negative 3.5. 1, 2, 3.5. Finally, 0 plus 0 gives you 0. So we have a wave down here. Now I know that looks a little funky, and listen, that's what it is. However, you can roughly connect the dots. You'll do at least as good a job as I do, so just try. Like up to here, here, come down here, got a little funny move in there, then comes down over here and up here. Okay, there it is. It looks a little nicer than what I drew, but you get the idea. That is the resultant wave. That is what we call the superimposed wave from A and B. Cool. Now, let's try this out. Here's a neat one. So here's the original wave. We want to draw another wave that will make complete constructive interference with it. Complete constructive interference with it. That means it should line up with it. Well, that's pretty easy. We want it to, like I said, line up with it. One option is it should hit a crest when the original hits a crest, which is right here. It should hit a trough when the original hits a trough, which is right here. Here, here, and there it is. That's not the only option, by the way. Are there other options? Sure there are. What would also make constructive interference with it is this. Here, 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 here. So, both of those would be a good option to make constructive interference with this. How do you know? Pick it up and put it on it. Boom, it lays right on it. There it is. This thing's going to make constructive interference. Now, how do you make destructive interference? The thing should be completely out of phase with it. So, what do you mean out of phase? It means when this one up here hits a crest, this one down here should hit a trough. So, 1, 2, 3, 4. Oh, that's ugly, but that works. What would also destructively interfere with this? This one would too. As long as the troughs are matching crests and the crests are matching troughs. Cool. So I'm going to show you some proof of this in just a moment. This wave and the original wave, this one right here, are called in phase, which gives you max constructive interference. This wave and the original wave being up here, are 180 out of phase, which gives you maximum destructive interference. So I'm going to show you a little bit of this in action. Actually, pretty cool. So we got a couple of applets that let us play with this. And this one, here we go. Let's see. What we're going to do is we're going to play this note. Let me lower it down a little. Sorry, volume. By the way, volume warning. I put a volume extension in here and put it down as low as I possibly could, but in case this is loud, be ready to adjust your volume. So here's F. Okay, now we're going to play the same note. There it is. Cool. So F and G, they just have as labels. We should just call this note 1, note 2. But there's the red one. There's the blue one. Now watch what happens if it's called a phase shift. You move it over so they play out of phase. Now here's F. Here's G. They sound the same. Your brain doesn't hear a different phase wave differently. Your ears respond to a crest and a trough, or a compression and a rarefaction the same way. It's just that note you're hearing. It's the frequency of it that determines the note, the amplitude, the volume. But whether it's up or down, or whether it's compressed or rarefied, your brain doesn't care. Now watch what happens when we play both. You may say, oh, that's just a computer messing around. Check this out. Let us put these so they're lined up, and let's play both. By the way, just F, just G, together. You notice it's louder, right? Well, it should be louder because they're on top of each other, so they're constructively interfering, and so the amplitude should get bigger. But now, let's extend the time and watch what we do here. We're going to shift one of them. Look what's happening. Uh-oh. It's getting quieter. They're more and more out of phase until they are completely out of phase. And bring them back. Still playing. Pretty cool, huh? So when they are 180 degrees out of phase, there is no note being played. There's no volume being generated here from the superposition. You literally hear nothing. And this is pretty cool. This is called noise cancellation or sound canceling technology. This exists. How do you kill a sound? You play the same sound at it 180 degrees out of phase. It's really neat. Look it up, sound cancellation. It actually does work. And it's not easy to make work. You need some sort of computer that picks up the original sound and plays back completely out of phase what it's hearing, so to speak. But a lot of your cars have this. Engine noises make pretty typical or pretty standard hums when they're on the highway. You have your speakers in your car, many of the newer cars, actually play that engine noise on the highway back at you, except 180 out of phase, just like this, and your engine sounds quieter. You don't even know what's happening, but it is. They call it ANC, active noise control. They do this also they try to do this with helicopters to keep them quieter if they're going into some sort of enemy territory. But it really is pretty neat. So I'm going to play it again. And you're hearing nothing because they're out of phase. But if you bring the phasing back, there it is, loud and clear. Pretty neat stuff, huh? Okay, let's go over here. Last question on this. Diagram shows two pulses, a square and a parabola. Which one represents a superposition of the two? Well, if you remember, this is all about amplitudes. You can get this problem. I mean, clearly, it ain't this one. They're not going to cancel. But how do you know among these? Like, what happens here? One way you might want to think about this, think of it kind of like sand. And the crayon will do for us. Think of it kind of like sand. Here's a beach with sand. Here's a block of sand moving toward a hole in the sand. And of course, the block will fall into the hole. So does it fall completely into the hole? Who's bigger? Well, the block is a little bigger, so you should have something left over. But the block is going to fall into the hole. Let me clean this mess up. But really, the best way to think about it is in terms of amplitudes. So here, if you notice, we have, draw a bunch of amplitude lines like right here, and then put another one, put another one. This almost reminds me of you doing your sum approximations in calculus, some of you. Okay, when this one comes over this one, we could bring this little guy over here. Check out what happens. We'll trace him. Are we tracing? Come on, crayon. There you go. Here's this one. Let's bring it over here. Good. All right, this one I miscolored. That was red. Let's make it red. What you'll notice here is that this one in the middle, there you are. No, not you. Well, this one falls down. This one falls all the way down. This one falls, not you, you, part of the way down. And the one in the end doesn't fall at all. And so what are you left with? The superposition, what's left over from these two, is this. You get this peak, and then it drops down, and then it comes back, and then boom. There it is. It's like Batman's ears. All right. So there's a lot of other cool stuff we can do here, which we'll talk a little bit later on. We'll do some of the advanced stuff. But that's it for interference. That's the basic deal. Now, we did interference because you can't really understand how instruments work until you understand interference. Now that we've got interference in place, the next thing we'll do is we'll start to talk about something called standing waves and how it is instruments function at all. Okay.